I'm Mark Weaver, Project Director for Retrofit for Saint-Gobain. Ably assisted today. It's going to be a threesome with Richard Fitton from University of Salford and David Farmer from Leeds, Beckett. Unfortunately, you don't get the chance to vote for us, so you've got all of us, so apologies for that, but you've got a chance to vote next week, so I'm sure you'll all be doing that. So this is a presentation on Salford Energy House and the work that Saint-Gobain did alongside Salford and Leeds in terms of using the facility and understanding the performance of the various retrofit products that we manufacture. For those that don't know Saint-Gobain, hopefully most of you will. One of the largest corporations in the world, one of the largest manufacturers of building materials. So some of the brands that you'll know in the UK include British Gypsum, Isaba, large manufacturers of glass, both flat glass for building and for automotive, which is Saint-Gobain glass. They've got a very large plant up at Eggborough. And also building material distribution, Jewson's, Graham's, Minster, etc. are companies within the Saint-Gobain group. And Saint-Gobain's vision is to be the reference for sustainable habitat, so buildings where people live, work and spend their time. It's about innovative products and high performance products, and obviously sustainable products as well. So that's a bit about us. One thing that we are as well is a founder, sponsor and partner to CORE. So we're very involved in the work that Peter's doing with the Retrofit Coordinator course. We're working with CORE to really help in terms of some of the content of CORE and also make our facilities available. So CORE courses are now being held at our technical academies in different parts of the country, as well as the Innovation Centre in London. So some of the research findings that we've got from the Energy House, we're working with Peter to bring those into the CORE diploma to help designers understand different principles of good retrofit. So just a very small bit about the different partners. So Saint-Gobain and the different brands that we have in terms of manufacture. It was our project that we undertook with the Energy House. Saint-Gobain R&D in Paris were very much involved in a lot of the testing, and you'll see a little bit about that in a second. Leeds Beckett did the monitoring of the systems that were installed, and obviously the facility is the University of Salford's facility, built in a, if people don't know it, built in a climate chamber. So why have we used the Energy House? Well, one of the principal reasons is that Saint-Gobain have got a very fast co-heating method called Cube, which allows you to do a co-heating test any time of the year within a sort of 2-day period, which is clearly a lot faster and can be run any time of the year, as opposed to the sort of traditional co-heating, which takes a lot longer. So the facility originally was, we wanted it as a really good test bed for Cube, and we've continued that development in 2 phases. But at the same time, because we needed to take a building from being non-retrofitted to retrofitted, it then gave us the opportunity to do 2 different stages of retrofit. So in 2013, which Richard will go through, we did a staged retrofit where we introduced products one at a time and then had a full retrofit result. And then this year, the back end of last year, we then did a final full retrofit using different products, using different baseline, which Dave will show you some of the early results from that. So I'll hand over to Richard to begin with, and he'll go through the first phase of testing that we covered.
Okay, my name's Richard. I'm from the University of Salford. I run the Energy House test facility. As Mark said, basically a test facility, we can measure any kind of retrofit product that goes onto or into a domestic dwelling. We've got kind of a long established, well, we've only been open for 4 years, so it's kind of long, relationship with Saint-Gobain in terms of testing. So Mark mentioned the Cube method of testing, which we kind of basically, that was our introduction to Saint-Gobain research over in Paris. The Cube method is, like Mark briefly explained, is a method of testing a whole building at the same time, but it does it relatively quickly, so it can do it over 1 or 2 evenings, basically, rather than the kind of co-heating method, which is 2 weeks. Possibly the co-heating method is a more defined test, or certainly a longer spanning and more further investigate test, but it's a very kind of quick snapshot of the cube. So that's basically where we started off with Saint-Gobain. And it was very much like a kind of baseline case as well to start off the series of tests which are on our now kind of our third phase with Saint-Gobain. So yeah, we've done quite a lot of fabric testing of solid wall insulation, which we'll discuss a little bit now. Okay, so the actual facility itself, the challenge we had when we kind of started to think about building this facility was what do we kind of put in it. Okay, so what represents the vernacular of the UK, which can be anything, let's face it. We have such a wide range of things. So then we came down to what's the actual issue in the UK, and Colin kind of picked up on it a little bit in the session we've just had. And that is, you know, we think hard to treat solid walls, you know, that type of building is the one that needs a lot of work, okay, a bit more investigation. The paradox being, the older the building, the more modern the technology, in my eyes, you need to kind of think about or put on the building to kind of get it working to the standards we need. So that was basically the building that we selected. And it was solid brick walls, suspended timber floors, lath and plaster ceilings, single glazed windows, largely uninsulated. The only bit of insulation in there as standard is just 100mm of token insulation in the loft. Modernisation measure that would have been done, you know, maybe the 70s, 80s, 90s. So I know obviously it's a terraced building as well, which introduces a whole other raft of issues into the whole kind of building physics behind it. So we've got to have this kind of neighbouring building. You never get a building like this on its own, going that shape and size. So we've got number one and number 3 dual terrace. So dead straightforward building. It's just bricks and mortar set in the middle of an environmental chamber. The environmental chamber is where the technology is and where we can actually think about kind of isolating some of the variables and putting variables onto the building. So we kind of, our temperature range is -12 to +30. When we're testing at 5 degrees, taken as an average kind of UK winter temperature, that's ±0.5 of a degree. So pretty accurate in terms of environmental chamber standards, and particularly when you've got a dynamic kind of hot block sat in the middle of it, pumping out kind of 10-12 kilowatts of heat as and when we tell it to. So it's a very accurate chamber with a dynamic load inside it. On top of that, we can put wind on it, rain on it, and snow, but we never find a kind of appropriate use for snow rather than just when the professors like to see it perform like a dancing monkey. So that's basically, they're the loads that we can put onto the building. So but as much as we can take them loads and put it on the building, Dave, you know, he'll introduce himself, but he does more testing out in the field than anyone that I've ever met in my entire life. And one of Dave's issues is the variables that are put onto a building outside. Okay, so when you're measuring buildings, Dave will go into the details. There's a hell of a lot of things that can affect them. What we can do, we can either put them on or we can take them away altogether. Okay, so we can take the weather off it as much as we can put the weather onto it, which again makes it a really accurate kind of test facility. This is the only one in Europe and the only one that represents our housing stock, i.e. brick, in the world. Okay, so it's quite a unique asset to Salford.
Is solar not important?
It is important. And in July, it will be installed. So you've got the chamber here. Okay, basically in July, solar radiation will be added. We will mimic solar radiation by using infrared heating all along the outside perimeter of that. I hate it. So basically, all around here, here, and here. And at the top as well, so basically the program, so we can track the sun around the building. We just won, I think it was 120 grand, something like that, to put that in, to basically add that in. Okay, so yeah, it is, because when we're talking about overheating, which is becoming a more and more popular thing to talk about, then obviously that's a big part of it. So yeah, this is like Saint-Gobain's second visit to the house. So we started off by testing the cube method and everything else, and then Saint-Gobain, kind of the material guys, so the guys from the UK and their R&D guys got together and started to discuss a test that they can do in terms of retrofit. So there's plenty of testing being done on insulation and things like that. What Saint-Gobain wanted to kind of take care of was a staged retrofit. Okay, so you put things on bit by bit, and then what was the big saving at the end, but what were the kind of elemental savings as we go through? okay, which is quite an important kind of revelation, if you like. And I'm sure Mark has got a copy of the report somewhere. We've got someone that kind of go through all those savings kind of item by item. But in essence, what we did, insulation-wise, we did EWI on the side, on the rear, IWI on the front to maintain that facade. We did some high-performance glazing, and we did some loft top-up. Okay, so we went from kind of 100 to, I think, 270. What Saint-Gobain disagreed with Salford on was the original standard of the building. Okay, we basically made pretty much worst-case scenario in terms of single glaze sliding sash windows. Saint-Gobain, and I attempted to agree, said, well, on a normal street, if we were to walk down it today, you're probably going to get kind of pre-2002, average kind of semi-poor quality double glazing in there, maybe a better standard door and stuff. So what they did, we basically put the old standard of double glazing in there. So pre-2002 U-value double glazed units throughout. So that was basically the baseline they set. So what they did is they made it slightly more difficult for themselves, if anything, because the base was slightly higher than it was originally. So the highlight of the test, and I'll say Mark's report breaks it down in a far more interesting way than this slide, is that we went from, so this is the whole house heat loss through the fabric of the building. So the original house with 90s double glazing, 100mm loft insulation, was 187.5 watts per Kelvin. Basically, when they did the full insulation, so that was EWI, IWI, floor and loft, and high performance glazing, we got it down to 69.7. So 63% in heat loss from the building. Okay. In terms of air tightness, we maintained basically a 50% reduction, and I think that came down to six for an air tightness test. So from a total, Dave, was it 16?
No, the baseline that was about 12.
12. Okay, the original baseline was 16.
Yeah.
Yeah, with the single place.
Yeah.
Yeah. So, I mean, it's a heck of a saving, and that's a good slide to put up. But I think that the more important part of what then learned from this was how the savings stack up, and like I said, the report kind of goes through that. It's never been done before, and it's certainly never been done under controlled conditions. And the outline of all of that test, in terms to wrap it up, was that the U values stacked up, the air tightness stacked up, and the model more or less kind of, I think it was in percent, Dave, was it?
Yeah, once the individual,
Yeah.
some of the individual parts,
The individual
about
measures,
1%,
yeah. 1% kind of variation. So I would disagree with what we just saw in the previous presentation. The fact that you can't kind of get solid wall insulation, you can. The fact is, we did it in a chamber, but we did it using bog standard materials, very bog standard contractors that needed some guidance along the way. Yeah. And you know, and it was an ongoing learning thing. It wasn't a gold-plated solution, and we kind of made sure that as academics that it was a kind of fair test. So yes, it can be done. There's still a lot of learning to be done. So the next test that Dave's going to present was a different style of test, taking a lot of different measures, more measurements. I think that the measurements we took for this was a ridiculous amount of measurements, and we more or less doubled it, I think, Dave, in terms of kind of sensors and measurements that we took. So the report goes into far more details about that original test, but you know, some significant savings, and it proves that if you do it right, it does work. But let's face it, the industry's still got a long way to go before we can do it right all the time on all the buildings. Okay, so I think it is Dave.
Yeah. Yeah, Dave Farmer. I test the energy efficiency of buildings routinely as part of my job as a researcher at Leeds Beckett University. We used to be called Leeds Met, so you might have heard about some of our work before in terms of areas to do with the performance gap. So today I'm just going to take you through the kind of tests that we performed on the building this time, and some of the methods that we used, and a brief overview of some of the results that we have come out of an initial preliminary analysis of the data. So it won't be going into the deep science behind it all. It's some of the headline things in terms of whole house heat loss, U values and air tightness. So there's still a lot more data analysis to be performed. So why do we get Leeds Beckett involved? Well, a lot of you might have seen a graph similar to this about the performance gap between the measured and predicted whole house heat loss of buildings. And the heat loss coefficient here in watts per Kelvin is basically it's the amount of power required to maintain a building at 1 degree above the external temperature. So if we have a building here at 100 watts per Kelvin, the blue, the predicted line there, so you need a 100 watt light bulb to maintain 1 degree temperature difference between internal and external. When we look at the red line here, we can see some of these are almost double, so obviously you've got implications in terms of whoever lives there, in terms of fuel poverty, in terms of payback times for lots of retrofit measured in terms of Green Deal. So we can go and do one thing, which is actually measure the building performance. But that's not always quite interesting, because when you do find these performance gaps, you kind of want to know why they've actually come about, what's causing the performance gap. So that's when, well, some people call it building forensics, or some people call it building pathology, it's all CSI type of terms, but what you can see here, it's clear this is on the new build, is that clearly this insulation is just going to get bypassed by air looping around the insulation. So it's quite easy to see, and certainly in this circumstance, why you might get a performance gap. Sometimes you have to go into other kind of more deconstructive methods, or some where we just use thermography where we're not allowed to take the building apart. This is for new build only, the graph, it's been updated. What you can see as well is that some of these where you don't have much of a performance gap, these are certain areas like passive house, where people put an awful lot of attention to detailing. So it's not all bad news, you can do it. The thing is about the performance gap is that it can exist in retrofit, the same things can apply, so poorly installed products, product substitution, people designing details which are unbuildable, and then end up something completely different happens on site. So there's a small evidence base for the retrofit performance gap, but we know it's there. So in terms of the measurement techniques we undertook at the Energy House, we did whole house heat loss measurement, so it's a co-heating test. Because we can keep the temperature steady in the chamber and steady internally, we can pretty much do steady state measurements with a very high degree of accuracy and a very high degree of repeatability between test phases, which in the external environment you'll do a retrofit and then you might find it's a lot windier one day, you might find it's a lot more rain, so these kind of things do cause kind of, well, there's more confounding factors you'll see in the external environment than what we find in the Energy House. So, Colin was talking about doing 8 or 10 in situ value measures being a lot. Well, we had 49 in the Energy House using heat flux plates, these little red discs here. They tell us the heat flow through an individual building element. We can divide that by the temperature difference, and that gives us an in situ U value. So there's 32 on the external wall. Well, you can read it there. That's where we concentrate in most of our efforts, because I tend to find that external walls are where you tend to find performance gaps are most prevalent. We also measured in heat flux on other areas of the building, so we weren't just looking at in situ U values, we actually kind of understand how heat flows throughout the structure, not just in the actual dwelling we're measuring, but in the neighbouring dwelling as well. Because I think Colin touched on it in terms of terraces, a homogeneous thing. Well, you can make an intervention on your own dwelling, and it can have repercussions on neighbouring dwellings, so we wanted to investigate that as well. In terms of other methods, thermographic surveys, see the bridging through the concrete there in the floor and the chamber. So thermographic surveys pre and post at each stage. Also during airtightness testing, so we do airtightness testing, but also when the building's warm, it's cool outside, you can see cool air being brought in. It's a good diagnostic tool for finding out any gaps in your airtightness barrier. We also did all models. There's all junctions, all 19 junctions being thermally modelled. On top of that, we're not just modelled to conventions, we're also modelled to the actual test conditions as well, which allows us then, with thermocouple arrays and some this black tape is here as a known emissivity, so we can do compare the thermal models with what we've actually measured, with actually what we measure in situ. The thermal models, when they're often built, they're a simplified measure, kind of representation of reality. So what you'll find often is it'll give you a temperature factor in the corner here, and we want to see how these stack up with what's actually being done. So whether it's a problem with the retrofit, that if it doesn't actually meet what the model is it a problem with the model, or are we seeing things in the building structure itself which might explain these. We also have installed some hygrotracks, which are wireless pretimeters. in the joist ends of the intermediate floor and the ground floor. And this was because right at the end of the test there was a humidity test as well to see whether the airtightness barrier was actually having an effect in those locations. Other investigations as well, performed borescopic investigations as well in areas where we need to see within the fabric. And we also did some construction observations. So a large number of tests to kind of get the feel about what's going on in the house. This was a slightly different test to say beforehand. It was an iterative test. This time everything was lumped together. It makes it a bit hard to isolate the effect of individual changes, but we look at it on a whole house basis. We've got lots of measurements so we can piece together through the thermal bridging, through the different thermal modelling, through the different heat flux measurements, so we can try and put it together. But we started off with a different baseline this time. So we had the sash windows in, which were originally there, and there was no insulation in the loft. The retrofit measures include on the floor 150mm of Celtex PIR between joists and a E-Server Vario membrane taped at the perimeter. The wall, 100mm of mineral wool held in place with its E-Server Optima steel channel system. That also has a vapour barrier on and plasterboard finish. The loft, there's 300mm of insulation put in there between joists and perpendicular, and just some double glazing units replacing sash windows. So we go on to the results. So you can see here some images of the retrofit measures. We take a baseline wall measurement of the thermal resistance of the wall. So we actually start with knowing what the wall was, how the wall was performing in the first place. And then instead of taking a value like you might get in RD SAP, we can actually take the actual measured value of the wall, and then from that, with the addition of the additional thermal resistance layers, we understand the total resistance, what we were expecting, and then we have a U value, a design U value of 0.27, which we were trying to achieve with the retrofit measures. As you can see here, we started off with the actual retrofit spot on. We haven't done the error analysis yet, but the number of measurements that we've made, standard on it is it's plus or minus 0.01. So it's we're pretty confident that it hit it. And the difference between the increase in thermal conductivity and what we actually measured was less than 1%. So it was a very kind of effective retrofit. Talking about the starting value as well, lower than the 2.1, which you heard earlier. But what Colin was talking about was different wall types having different U values. In this wall here, it's all the same house, built by the same people. We've had a spread of U values at distances that weren't affected by thermal bridging, which is all these measurements here are, of between 1.56 and 2.17. So even if you think you understand the wall type and what's going on there, you can still get a very large spread. So there's a bit of, you've got to be quite cautious when just taking one or two measurements on the same wall itself. So success story with the divide. We haven't got a big evidence database, as I say, with Retrofit IWI. We've done some tests, the Deck Green Deal project at the moment. Here's another couple of IWI systems. Both of these were PIR IWI, but as you can see, we found a performance gap in both those. So there's not really much to compare it against at the moment, but as I say, it seems like a successful retrofit. In terms of the other measures that you guys have measured, the ground floor, you can see the retrofit in progress there. Thermogram was reasonably consistent across the ground floor itself. We did have a little bit of extra heat loss at the perimeter, which you'd expect, especially around the air bricks. In terms of the increase in the actual retrofit value, 0.11, that's lower than I calculated. Unless they've put extra product in there, you can't kind of beat reality. What we explained is that's either within measurement error, or it's also there's actually been a fundamental shift in the performance of the behaviour of the floor itself. So a narrow floor depth, the ventilation characteristics have changed within that, so there's some greater analysis to be done. But it would appear that the floor performed as expected. Loft insulation, the calculated value is 0.12 from the retrofit. The mean of the values that we measured was 0.20. unfortunately, the Energy House has got, it's got a very shallow pitch roof and also a lot of extra roof timbers in there, which meant that in a lot of locations, as you can see here, these timbers that you wouldn't quite expect, you can see heat loss in these areas here. So areas where we didn't find that there was any obstruction in the loft, we actually did measure a U value which was comparable with the design U value, but as I say, the problem was here in the loft. But I guess in any loft you're going to find problems anyway. It's not just going to be the Energy House loft, there's going to be unexpected timber fractions, there's going to be all sorts of rubbish up there, shallow pitched roofs. So I'll say the headline there is not such a bad problem for Saint-Gobain. We often find anyway that loft insulation, when it's installed properly, we very rarely find a problem with the install value. And the double glazing, that's another one where we very rarely find problems. We've got a value of 1.40. And nice to see around the window as well that it doesn't seem to be too much of a problem with thermal bridging around there. They did insulate the reveals as well, which to a high standard, which we're doing some more analysis on that at some point. In terms of airtightness, the baseline was 15.4. That was a lot higher than last year's baseline of 12, but that's because of the sash windows and the doors. So this was the only kind of test where we were able to do it in some iterations throughout the retrofit programme. What they did was they put in all the retrofit measures except the floor membrane. Well, so anyway, we'll stop before we start there. Yeah, 63% reduction, and I think I've got 63% reduction down to 5.6. It's quite comparable with the previous retrofit as well, which, I mean, you can't make too many assumptions off only two retrofits, but it's kind of saying go in, do a standard retrofit on a dwelling such as this, and that's the kind of area you're going to get with this individual dwelling, this value for air permeability. So just the initial retrofit measures themselves, we measured a 41% reduction in air permeability. We think a lot of that was to do with the installation of double glazed windows. They also, within the floor itself, between the floor joists, there was PIR rigid board between the floor joists as well, which will also increase the air tightness slightly as well. Loft insulation might have made a little bit of difference to the resistance of the air path coming through, but not a great deal. If we look at before the floor membrane goes in, this is on the stairs, here's two spine walls, and you can see the junction here with the floor. Under depressurisation, you can see an awful lot of cool air being drawn from the underfloor void into the actual into the habitable space. Following the introduction of airtightness membrane, you can now see that most of this problem is gone. There's still some problems where you've got detail up in the corners and hard to treat areas, which you might often find. So that's an extra 28% from the previous value, just from the introduction of floor membrane. In the past, in the previous test where we measured 42%, that was including the floor insulation as well. But it's our kind of experience at Leeds that any house with a suspended timber floor, whether it's a cellar or a floor space below, houses which achieve the best reduction in air tightness, improvement in air tightness, are the ones where people deal with the floor, especially at the perimeter. So following the floor membrane being installed, we did another set of leakage detection, and the installers went round, and that actually showed them some areas that they'd missed. So they were able to go in and do remedial work on areas that they'd missed. So what you found here is that another 16% reduction was achieved. Last year we did the same thing on it and we measured a 13% reduction. So what it's saying here is that you've got experienced kind of people, some experienced people coming in, and they'll quite often not miss something. When you're building a new house, you tend to draw the air tightness barrier on beforehand, and you can kind of look for it in the process. With existing buildings, you tend to find air paths that you wouldn't have actually thought about, and every job is different. So people are coming along and they're finding things they don't expect. So a couple of things about the air tightness really is that, first of all, doing the air tightness check prior to actual finishing it off does allow people to actually rectify any problems. It allows you to understand whether you've actually kind of made something too airtight and ventilation might be a problem, or whether you've not actually got it down to your target which you actually required. So I would suggest that, and also that when you're kind of designing an increase in thermal performance, To do a calculation in terms of the increase in resistance of a wall or floor, it's quite simple. With the airtightness, people often have a target, so say with Retrofit. How do you get that target? You know, how do you know you've got that target? I think until they've got, with U values, we haven't got this very quick diagnostic tool yet, but with airtightness we have. And I think you can go around your building with a lower door kit until you actually have made that building get that airtightness strategy you want. So I'm not advocating, it'd be good to do it on all retrofits, but I'd definitely advocate it for people who are wanting to do what you might call prototypes. So if you've got a large number of a certain type in your housing stock. It also, I found that when we've done these things, that contractors have actually it's actually made them think and understand about the air the actual air paths that exist within buildings and how they might actually go about looking at how to fix these in future. So it's not just about getting value, it's about showing the people who are doing the work what kind of things to expect and look out for. So in terms of whole house heat loss, we measured 75% reduction. That's a 229 to 55.1, which is it's substantial reduction in heat loss from the whole dwelling. It's fabric heat loss. What we haven't got at the moment is another bar, which is a predicted value. We need to do all the thermal modelling of the junctions at that point, and then understand what the predicted value of the building is and how far away it was from what we predicted. 75% reduction is good. Similar reductions, obviously, in the annual space heating costs and CO2 emissions associated with space heating. And just to wrap up, this is substantial improvement in thermal performance. It was done relatively quickly, it was done with standard materials, and it was done with a contractor as well. It wasn't actually done by the ISO itself or Saint-Gobain. And I would say, we talk about a lot about numbers, but let's talk about with the building pressurisation tests. I think that's a good one for process that should be possibly included in more people's retrofit strategy.
Thanks, Dave. So just to wrap up in summary, then hopefully you've seen the sheer level of detail that we went into on this house, and also clearly the house next door as well. That's one of the reasons for us really wanting to go there, because we could actually observe what was happening in the neighbouring property as well. So you've seen the sort of level of data that we've collected. There's more to be done. But the overall sort of message that we're using from both phases is that really impressive performance can be achieved from what are conventional off-the-shelf systems with contractors that, with some training, with care and attention, etc., can deliver excellent results. And certainly, I won't say calls into question things like in-use factors, but it demonstrates that actually the levels of performance that can be achieved by these products can get very well, in fact in our cases at the predicted levels. What are the unknowns are things like the walls values to begin with, as Dave said, because they're quite clearly quite varied. There's more phase 2 data to be analysed, which Dave's already touched on, so more thermal bridging calculations, and also we took some thermal comfort readings about actually how would the different rooms feel to occupants in terms of things like air temperature and surface temperature of the walls, the windows, etc. So there's going to be data coming out on that. We're also doing, we accept that with the energy house, it's obviously not in the field, so we're doing field data testing as well on properties and some of our different systems and solutions. So for those that were at yesterday's presentation when we were talking about moisture and things like reverse condensation, well, we've done a 2-year study on that on our internal wall, one of our internal wall systems, and the results that have come back are excellent. It's with products that have been in the market for 20 years. They've been developed in Germany, who have had exactly the same issues. So you'll see some evidence coming out from the testing we did there. And I think if you put the energy house and the field testing together, you've got a really good complete set of data, and it does determine or does illustrate, as Dave and I think Richard both said, really good performance and good standards can be achieved with care and attention, with support and thought, and doing things as we say, like some airtightness testing to see if you can just push it that bit further with quite simple interventions. One thing we're really keen on is, and that's why we're partnering with Core, is how we get this knowledge into the installers and to the designers. We do an awful lot of training, We've trained in our systems for years and years, and that's why we have the technical academies. This is additional input that will go into that training, and hopefully with the work we're doing with Peter to go into some of the retrofit coordinator work. We do have a real issue with PAS 2030 as a manufacturer, because we don't believe it's really fit for purpose. There are too many light touch approaches and too many ways in which contractors are not monitored in terms of their competence. So we're real advocates of things like NVQ training and giving people actual, real qualifications on the measures that are installed. So rest assured, that's something that we're really pushing hard to raise the bar for the industry. And any further information you want, speak to us today, or if you go on our website, you'll see increasing evidence of the work that we're doing. So that's it in terms of the presentation. Time for any questions, I think, until we get a knock on the door. So,
how do I specify thermal board insulation that's pre-shrunk, off-gassed?
Well, talk to our companies that that manufacture them. I think as we've seen already with some of the presentations, it's about understanding the right product for the right circumstances and the right building. So we've got within our group a range of different solutions, both closed cell and open cell, and I think that's where our technical teams can support you in understanding the best specification for the particular building and the circumstance that you're in. And we're all learning, as we've seen, the constituent parts of retrofit in terms of the original building. There's an awful lot of understanding that's needed, and we want to be at the forefront of that understanding.
But knowing the issues that would bring up with thermal bridging, are you at Saint-Gobain still selling thermal insulation board which hasn't shrunk yet due to off-gassing? Because surely you should be stopping that and only selling insulation which has already shrunk due to off-gassing.
Actually, in terms of sort of the technical performance of our system, you'd have to talk to that particular brand. So it's not a question I'd duck, it's just something that I'd refer you to the manufacturers of those. Celotex is the manufacturer that manufactures PIR for to address that question with them, because as I say, they're more than capable of answering it, and clearly their insulation is for different parts of a building and for new building as well as existing. So as I say, not the right question for me to answer, but certainly I'd refer you to them, and more than happy to take your details to for them to discuss that with you. Peter?
Both Richard and Dave had some fuel cost savings on the slides, and I just wondered under what occupancy assumptions for the cabin. Do you simulate the occupancy of the house, or do you just use a calculation?
Yeah, there's I mean, I'm always dubious about any kind of assumptions in terms of, we have to use a standard methodology which is just based on degree day data. It's also based on the use of a gas boiler at 82.5% efficiency as well. So they're very simplistic calcs, but the calculations can be... Pardon?
Intermittent heating, or?
It's just based purely on the degree day data, so if the number of degree days...
so basically you give it warm all the time?
Well, any time it drops below 15.5 degrees, yeah.
And I suppose to some extent it's the difference from before and after that we're really looking to measure, rather than... Yeah,
I think it's quite important to understand more the savings and where they actually came from.
It's in the reports. That is underlined in terms of like where the assumptions are.
Yeah. Richard, can you simulate occupancy in the house? Can you put
Yes,
people simulations?
It's difficult to do, but it's the same as kind of when you kind of take it back to a SAT model or something. It's trying to work out what occupancy you want to simulate. But yeah, in essence, you get what's called DIN men. So basically, it's white or black tubes, depending on who you listen to, with a kind of 3 lamps in the middle, and you control the number of watts that gets output from them. So yeah, we've got some testing coming up that we're going to use.
And that's going to be watts for people cooking.
Yeah, people, lights, whatever. Yeah, but and obviously then it comes down to where you put them in the house and things. So yeah, it's again, there's no the air conditioning guys using far more than we do in terms of heating watts. So they've got a kind of standardised methodology. But yeah, again, it's an assumption that you have to make, and it's quite a difficult one. But you've got to.
Now we've got the first cut of data, then we can go into actually looking at different sort of patterns and trying to mimic occupancy. So, one final question.
The benefits of these sort of things are that they're repeatable in the real world over and over again, 5 days a week, 12 months of the year, and that they perform over time with occupancy, weather and shrinkage and all the rest of it. and that any of the product failures or lower performances don't end up with the sort of problems we saw next door earlier. Is there an ongoing look at it, what happens over time, that these things will still perform? Okay, there probably will be a drop-off in performance, but that we don't end up with the condensation, the cold bridges, the gaps, with any of those things that are
I
failures.
mean, not in this particular facility, obviously, because we've had to strip everything out. We have to return the house to how Richard's, to Richard's high standards and requirements at the end of it. But there are other tests that are being undertaken to understand the long-term performance.
I think the way I would answer that was and Dave covered it slightly with his thermal bridging work, is the fact that a lot of it's about informing models with real world data. So, we've got an IES model that's perfectly tuned, we've got, roughly with some good kind of Salford weather data as well, which is difficult to come by. But I think what you can do is if you can verify a model, and roughly it's kind of, good kind of, it's okay. But if you can put good data into it, in terms of what your actual surface temperature was at that exact temperature in that time, and this, that, and the other, then you can actually start to build your models up to a more long-term forecast. I think that's probably as best as we're ever going to get, because when you're out in the field, there's so many variables, it's very, very difficult to measure. But I'm a big advocate of building a few test houses that have been retrofit, stick them in the field and see what happens.
Perhaps
we
we
can't
can
do that.
A core fellowship visit to
Yes.
the facility.
Yeah, absolutely. Yeah, you're more than
Others.
welcome.
Are we going to have to call it?
Yep.
Thanks, everybody. Thank you.
Let's